Alrighty, welcome back to operating systems. So today, review time. So this is what? Ooh, echoey. This is midterm eve. So on midterm eve, what do we want to go over today? I am here for your benefit. Any other words I use sound weird, so I won't continue with that thought. So, what do we want to do? Or I'll just slowly leave. All right, any special requests? Yeah.
For the UCLA midterm
Uh-huh.
page table question.
UCLA midterm page table question.
Yeah.
Is it the fall one? Is it the fall one?
The one you have on the slides.
Yeah, it should be the fall one. Midterm, no. Is it this one?
Yeah, I was just wondering where the offset bit came from.
So where the offset came from?
For the second question. Like the level equation?
Yeah.
So it's like the virtual, it's minus the offset, right?
Yeah, so the wording on this was kind of bad. By 2 megabyte pages, it probably should have been rewritten to, instead of saying pages, to say page size.
Oh, okay, I thought it was just like to the 21 pages.
Yeah, no, it should have been page size. I should have written it better, but you know, yeah.
The number of offset bits is always just going to be the size of the page.
Yeah, so it's where you are within a page as long as the page size is in bytes. I mean, I could be really weird to you guys and say the page size is in bits. I don't know why I would do that, just to make you divide by 8. But if it's in byte, it has to be byte addressable, so it's just however many bits. Yeah. Mm-hmm. Yep. Yeah, so you always want to multiply by the number of page levels of page tables you have because it's a separate memory access for each one, and then the original one. So this exam was a closed book exam, so I gave them the equation, but I also said that recall for a single page table, this is the equation, so that's where the 2 came from. And then I was like, oh, calculate it for your multi-level page table. So you had 2 levels, so 1 for each level plus the original one, which is why this was 3 here. Yep. Yep.
By the original one, you mean like actual memory you're accessing?
Yeah, the actual memory you're accessing, like that physical memory. So, yep.
Are they the same times in practice, like the memory access for physical versus the page table?
No, they wouldn't be at the same time. So like
Like they take about the same amount of time.
yeah, because they'd all be physical accesses, right? So they'd all take the same amount of time, but you can only access physical memory anyway, so. All right, so, wait, let me switch so I don't show you anything I shouldn't. So if everyone does not have any preferences, let's see if we can find a good one here. Nope, that was too far. All right, people seem to like doing virtual memory in like a certain sense. What about this? So have we seen this question yet? So you can go and look at the final for 353 as well, and the final for 111 if you want. And some of the questions are going to be valid for you. So this is from 353, so their final exam, and there's a virtual memory question which you should be able to do, so you might not have seen this yet. So we can do this. So, so we created a very silly machine. This silly machine has 12-bit virtual addresses, 8-bit physical addresses, page size of 16 bytes. So whenever I see a page size in bytes, I should probably just write it in powers of 2 because I'll probably need it. What's 16 in powers of 2? Yeah, 4, 2 to the power of 4. So without even reading the question, I'll just put 2 to the power of 4 here because I will probably need it later. And then the page table entry size is 1 byte, which, I mean, you can just do 2 to the power of 0 if you really want. But we're going to be multiplying and dividing by 1, which, I mean, you don't have to do anything. But hey, if you want to get in the habit of writing it, go ahead. So it says our page table entry has the following layout. So remember what is in a page table entry. The important things is that it has the physical page number, and then it has some permission bits, which it would at least need to have a valid bit. Likely, it probably also has a read and a write bit, and then an execute bit or something. At the very minimum, though, it would need a valid bit. Here, I just created 4 bits for the permissions. So you might notice here that this system is overly nice to you because you don't actually have to write anything out in binary because it kind of nicely matches with hex numbers. So this is our 8-bit physical page table entry. So 8 bits because it is 1 byte. So the last 4 bits are the permissions here. And they are 4 bits, which would be exactly 1 hex character, so you can actually read it. And then the upper hex character is the PPN, which is also 4 bits here, again, to make your life easier. So given that information, I also give you a giant dump of physical memory. So this is like the base address here, and then the columns are like the offset. So if you want to know what the value, the byte is at address something like, I don't know, 03, well, you would go in this column, and 0 plus 3 is 03, so the byte there would be AF. If you wanted to look at what the byte is at address 24, well, you go here. So it starts off at 2, and then plus 4, you would get this byte. So at address 24 in hex, you would have the byte 3F. So any questions about reading just the dump of virtual memory? Or no, sorry, this is physical memory, physical memory. Yeah.
Wait, so the PPN base, or the base address is 2 hex, right? So 2 hex.
Yeah.
So
So,
that's 8 bit.
yeah, so in this, like every column is 8 bytes here because I can only fit 8 on a page or on a row.
But the PPN is 4 bits. So how would you represent that address with just 4 bits?
So the PPN is 4 bits, which means it would start, like if you have a PPN of 0, it means that, well, all address 00 in this case, so offset 0 all the way to the max. All of those addresses would be on the same physical page, right? Which would be 16. So if I want to, another easier thing to do might be just to take this memory and everything will be page aligned. So I'll just divide it into pages. So essentially, since my page size is 16 bytes, I can just divide it into groups of 16 bytes. So something like this. So everything here would be on physical page 0. All these 16 bytes would be PPN 1. This would be PPN 02. This would be PPN 03, something like that. So if you look at memory like that, well, there's 4 physical pages, 0, 1, 2, and 3. So any questions about that? All right. So first question is, how many bytes do we need to store a single page table if we used it? So here we have 12-bit virtual addresses, 8-bit physical, and page size of 16 bytes. So if I have a single large page table, I need an entry for every single virtual page number, right? How many virtual page numbers do I have in this silly system? So how many virtual page numbers do I have in this silly system? Yep. 4,096? How'd you get that? So to the 12, that would be my entire virtual address space. So then I have to take that and then divide by the page size, right? No, so this is just a single large page table. So if I have a single large page table, I need an entry for every single virtual page number. Yeah.
So if page size is 16 bytes, that's 2 to the power of 4, so we need 4 bits for offset, and then 8-bit physical address, so then 4 bits are used there, so then 4.
So not related to the physical address at all. So in this case,
So then it's 2 to the power of 8, right?
yeah, so to the power of 12 is like how many bytes I can use for all my virtual addresses. Then to figure out how many virtual page numbers I actually need to support, well, I just divide that total by the number, or by the page size, which is 2 to the 4. So that means I need 2 to the 8 virtual page numbers in my giant page table if I just use a single page table. So that's how many page table entries I need, and then if I need the total size of that, well, I take this number and then multiply it by the PTE size. What's the PTE size in this in bytes? 1, so I can just leave it alone. So in this case, it would be 2 to the 8 bytes. So I would need a single page table that's 2 to the 8 bytes because I need 256 entries. All right, any questions about that one? Yeah.
So I thought of it differently. I also got CPA just now, but I was thinking of it like it's 2 to the 12. Like the virtual address is 12 bits, and then because the physical page size was 16 bytes, you needed 4 bits for the offset. So you have 8 bits left for virtual memory.
Yeah, so you can also think of it that way. So if you want to, instead of just thinking about how many virtual page numbers I want and doing the division, well, you know you have 12 bits for that virtual address in total, and then you know that, because of the page size, 4 of those need to be offset. So you can also just do this and figure out that. At the end of the day, it's the same thing. So just P2 that number and then times the page table entry size, which might be different. Yeah.
Yeah, so, in some questions, when you have a virtual address, there will be some number of bits that are unused. So is it like just a safe assumption here that you're using all of the bits?
Yeah, we try and use all the bits here.
Okay.
Yeah. Yeah.
I guess there's a question when there's unused bits and we clarified, right?
Yeah, so if it's like a weird number, like it might be like, the only time you have unused bits typically will be if you have a multi-level page table and they don't quite line up exactly, and then you would have some bits that are unused because you don't support that whole virtual address space, but that's like the only exception.
Gotcha. Okay.
Yeah.
Can you quickly remind your way of remembering 2 to the power of what is? I remember you said that.
Oh, the tricks. Yeah, so the tricks. Yeah, I can only divide by 2 and multiply by 2 like at most 2 times. So the only things you need to remember, 2 to the power of 0 is 1, and then 2 to the power of 5 is 32, 2 to the power of 10 is 1024, and then you can figure it out from that. So 2 to the power of 8, oh, well, I only know 2 to the power of 10, which is 1024. To get 2 to the power of 8, I just divide by 2 twice. So 512, 256. Yeah, or put a table on your cheat sheet, or I guess you're allowed to bring a calculator if you really want to too. But you might be wasting time than just by knowing powers of 2. So 32 to the power 5 is generally the only one we should need. All right, so yeah, then the question shifts to the more fun part because single level page tables are lame. So we could do multi-level page tables. So next question is, what is the minimum levels of page tables we need in our system, assuming that each level of page table exactly fits on a page? So anyone remember how to do that?
So like each page is 2 to the power 4.
Yep.
And the page entry is like 1 byte, so it's 2 to the power 0. So which means we have like 4 bits for the. So each page contains like 4 bits. So we have like 8 left. So it should be 2 level page.
Yeah, so in general, remember the number of levels we need is like the ceiling of virtual bits minus offset, divide index, and to figure out the number of index bits we need to figure out how many page table entries we can fit on a page. In this one, well, because every page table entry is just 1 byte, well, I can fit 16 of them on a page. So my number of index bits is just 4 in this case, same as the offset bits. So in total, my virtual bits from the question is 12, offset is 4, and then my index bits are 4, which would give me 12 minus 4 divided by 4, which is 8, 4, and ceiling. Luckily, that's a nice number because I am so nice and it's just a 2. So we need 2 levels of page tables for this. Any questions how I got that one? Yep. So the index, remember the index is essentially depends on the number of PTEs per page. If I know that, that would be, and turn that into 2 to the power something. If I log 2 that, that's how many bits I need. So in this case, it's always the page size. Oops. It's always the page size divided by the PTE size, just like it was just a giant array. But in this case, my page size is 16 bytes, and then my PTE size is just 1 byte, so I don't have to change anything. But in general, that's the equation you gotta use, because it's just a big array. All right, are we good? 2 levels of page tables, all good? All right, so here's where it gets more interesting. So we're going to translate virtual address 1, 2, 3. So in this virtual address, we have 2 levels of page tables. So I should have an L1 index and an L1 index and an L0 index, and then an offset. So in that virtual address, 1, 2, 3, which number is which? And luckily, you will also note that I was nice to you, and you can just leave it in hex. You don't even have to translate anything, because in general, sometimes they don't line up nicely with hex numbers, and you have to write it in binary, and it's just a complete mess. This one is nice because you don't have to translate. So which of these hex characters is the L1 index? Yeah, 1, right? So this is our L1 index. 2 is hopefully our L0 index. And then 3 is our offset, right? Any questions about that breakdown? So that 1, 2, 3, boom. That was 3 questions. Basically tells you to read it. All right, any concerns about that? Okay, so then it said, for this virtual address, we'll try and translate it. So either the value of the final PTE if it's valid, and otherwise the value of the PTE that causes a page fault. So another part of this question says that the L1 page table is at PPN 2. So I will highlight it in cyan. That means these 16 bytes here, that represents my L1 page table. So in this L1 page table, if I'm translating address 1, 2, 3, what index do I use for my L1 page table? Well, it should be index 1. So where is index 1 on physical page 2? Yeah. 1F. So that's where index 0 is. Everything is a byte, so there should be 16 entries in this page table. This would be entry 0, 1, 2, 3, all the way up to 15 here. So if we're translating that address, well, the L1 index is 1, so we would look at the byte at 1F. And then this, we know, is our PTE. So since this is our PTE, is this a valid page table entry given that layout of our page table entry? No? No, it should be, right? So if we take this 1F and then translate it to that over there, well, 0001, or I could just leave in hex, I'll put in binary because sure, whatever, is the PPN, and then the rest are the flags. So the execute is 1, write is 1, read is 1, and valid is 1. So all of its flags are valid, so it is a valid entry. And since this is an entry in our L1 page table, what does the PPN tell us? Is that the PPN of this virtual address? No, it's the PPN of L0. So that means that, let's highlight it in green, that these 16 bytes represent our L0 page table, right? So in our L0 page table, what index should we look at? Well, we're translating virtual address 1, 2, 3. So our L0 index is 2. So if we look at page 1, this is at index 0, this is at index 1, this is at index 2, so it should be this byte, right? Any arguments that that is our page table entry in the L0 page table? Yeah. Oh, that one. Why did it just erase a bunch of stuff? Can I go back? There, that's better. So it's,
Walk over the whole procedure again?
yeah, so whole procedure again. So the question tells us we are translating virtual address 1, 2, 3. So that also translates into we have to use 1 for the L1 index, 2 for the L0 index, and then when we're translating it, we don't have to touch the offset. And the question also tells us where the L1 page table is. So the L1 page table is at physical page 2. So that corresponds to that thing highlighted in the cyan color. And since we have to, for this virtual address, we have to use index 1, well, we look at the index 1 entry, which is this, whoa, that was a bad tool to use, which is this page table entry. So since that was a page table entry in our L0 page table, we can check. Why does it keep erasing it whenever I look away? So this means if we take this and break it out into the page table entry, it means that execute was 1, write was 1, read was 1, valid was 1. So it's a valid entry. So the physical page number is valid and it points to an L0 page table. So it should be at physical page 1, which would be what's highlighted in green now. So then that's my L0 page table. So because I'm translating that address, I look at index 2, and then the physical page, or the page table entry there is FF, which is valid, and it corresponds to physical page F that we haven't used yet, but that's the physical page number, or page table entry we would use as our final translation. Because this is L0, we're done, right? So the answer to this question would be like the final value of the PTE, if it is valid. It was valid in this case, and the final value was FF. Yep. If there is a page fault? Yeah, so if there was a page fault, I mean, I could just make one by just doing this. So in this case, if I just change the page table, the first page table entry in L0 to just not be valid, there'd be a page fault in L1, and that would be the failing page table entry. I would get 1, 0, because that valid bit would be off, so it's a page fault, it's not valid. The rest of the value, yeah, if valid is 0, you don't read the rest of it, it just fails immediately. All right, any other questions about that one? All right, so what is the final resulting physical address then? So we were translating address 1, 2, 3, and then our final page table entry was FF, which means it was valid, and the PPN was essentially just F. So what is our final physical address going to be for 1, 2, 3? Yeah. Yeah, 0 hex F3. Because remember, essentially what we're doing all the time, no matter how many levels of page tables we have, is we're taking the virtual page number. Whoa, that's some good writing. So we take the address, we divide it into the virtual page number and an offset. In this case, our virtual page number was 1, 2, and our offset was 3. And then all the time, no matter what, when you're translating it, you're just translating it to an offset and then a physical page number. So no matter how many levels of page tables you use, it's all the same idea. It's just how many steps you need to go through to actually get this physical page number that you actually want that is your translation. So after 2 steps, we figured out that the physical page number is just F. So 1, 2, 3 would translate to F. Whoops, wow, that's a big eraser. So we don't touch the offset. So we figured out that virtual page number 1, 2 corresponded to physical page number F. And we don't touch the offset. So that means the final physical address is just F3. So any questions with that one? And hopefully, yep, we were correct. I still get to teach. Yeah.
Why do we have only one F right now?
Sorry?
Why do we have only one F?
So why do I have only one F? So this right here is the entire page table entry. So that FF is the page table entry. So given this, it's divided into 2 parts. So the first hex digit is the PPN, and the last one is all the permission bits. So in this case, the layout of this also doesn't matter. I could have flipped it if I really wanted to, and could have had the permission bits first if I want. As long as you're consistent, it doesn't matter. All right, any other questions? Someone pasted a question that looks real fun. Yeah.
What kind of answer would have caused the page fault here?
So yeah, a page fault would just happen if at any stage in the lookup, the valid bit was 0. Or if I was really mean, so the first entry we looked at is like 1F. Some of the questions are like fun, where like they'll put an entry here that's like 8F, so that's valid, but you have no idea what that memory actually is. So like the answer could be like, oh, it's out of range, I can't see what it is. Yeah.
It wouldn't be possible to have it like, what was it before? Like instead of F for the second one, you put like A, because that's 1010, so valid is off.
Yes. So if I change it to 1A or something like that,
That's not possible, right?
yeah, it would correspond to A is just 1010. So that means the valid bit would be 0, in which case nothing else matters.
But then, yeah, that's true, but that wouldn't ever happen because valid, like read would not possibly be 1 if valid is 0.
No, so in this case, for real systems, this is totally possible. So your MMU, it just checks the valid bit. If it's 0, it just ignores it. So this is actually a way we'll get into later. The operating system can actually take advantage of this. So that means if it's valid, you can store whatever the hell you want in the other remaining bits, and you can use it for whatever you want. Yeah.
Then how come like the final physical address was F3, but is that not out of range on this table, or are we not?
Yeah, that's just the final physical address. I didn't say what the value is or anything.
Okay, so that's fine.
Yeah, that's fine.
But if you ask the value, you wouldn't be able to find on this table.
Yeah, if I ask for the value, it's like, F3 is the address of a character or something like that. And then if I ask what's the value of the character, the answer would be like, I don't know because you didn't tell me. All right, anything else? So let me go back. So there was a fun question that was posted in the Discord that kind of looks like, well, this one too. Whoops. So if you want, we can do this question, but it's from the 111 fall final. And this is technically within scope for you guys because it includes threads, but not data races or anything like that, and processes. So we can take a gander at this. Let me know if you want to go over this one or not. And spoiler alert, your exam kind of has threads on it, but it's not terribly big. Yeah.
What's the question from?
So this question, basically it just says, it's pretty much just explain everything that happens here. How many processes get made for this print statement? Show me all the results from this print statement. So, want to start going over this and stop me if you get bored to tears? All right. So let's just walk through what this program does. So let's assume that we execute this. We're executing, I don't know, process 100. It starts executing main. First thing it encounters is a fork. Oh, yeah?
Sorry, just one question. If it's not explicitly stated what the PID of the currently running process is, do we just assume any number we want?
Yeah. Yeah. If it's not stated what the running process is, state whatever you want, as long as it makes sense.
So you can say init, like 1.
Yeah, if you say 1, I might be like, that's kind of weird, but it might be okay. But generally, 1's the only one you should really avoid, because we kind of know what init does. So in this, yeah, I think all the time I specify a starting one just because it also makes it easier to grade and more consistent. Typically, I always say it just starts with 100. Why do I like the number 100? I have no idea. So in this case, we hit fork immediately. So what does fork do? Everyone remember? So we create a new process, right? Probably gets the ID, I don't know, 101. So they're going to be exact clones of each other. Right now, they're both executing main, so nothing fairly important happens. So we'd have process 100 and 101. And if I draw, let's say I draw my family tree up here. So I have process 100. 101 should be a direct child of process 100, right? So this is what my family tree should look like. Any arguments? Should it also do that? That's like the royal family tree, so we don't want that. All right, so now we have process 100 and 101. They are exact clones of each other. The only difference is going to be the return value of fork. In process 100, what would it get returned from fork? 101. And then it would create a variable called PID and then assign 101 to it. In process 101, it would create PID and it would get assigned 0, right? So now at this point, is process 100 guaranteed to run, or is it left to the computer gods? Yeah.
I mean, you created thread 1 first, so that calls the run function on the creation of the thread. So shouldn't that run?
So that just creates a new thread, and then kernel's up to schedule it as much. Yeah, so it could be a queue if you did your own, but in general, you can't guarantee it's a queue. So if it's just a generic kernel, you just have to say whatever the hell could happen. Because, well, if this is Linux, it's a completely fair scheduler. Maybe you ran out of your time slice already and it switches you immediately. You have no idea. So at this point, we have no idea what runs. Say the main thread of process 101 continues executing. Well, it will hit pthread join of thread 1, and then it will be blocked, right? So the main thread of 101 is blocked, waiting for thread 1 to what? To finish or terminate, exit, whatever you want to call it. So at this point, well, also if I wanted to, the main thread of process 100 could run, but that would probably make this even uglier than it already is. So at this point, the main thread of process 101 is blocked on that pthread join. So let's pick. Do we want thread 1 or thread 2 to run? Because it's up to the gods now, we have no idea. Thread 1? All right, so thread 1 runs. Oh no, it calls fork. Anyone remember what happens if you call fork and you have multiple threads running? Yeah, so you still create a new process, but that new process only has a single thread of it, which is a clone of whoever the hell just called fork. So in 101, also have a variable when thread 1 called fork, the new process is an exact clone of that thread. Yep.
Process 102 only exists in run, right?
No, so process 102 exists through run. So it is, because all these threads, like thread 1 and thread 2 in this case, are running in process 101. So if you wanted to, another thread could wait on 102 or something. It's still available because it's still your child process, just another thread made it.
Oh, so you don't have to join process thread 1. Process 102 exists.
Yeah, so process 102 is just a completely independent process that just keeps on executing. So here, if we want to write out what threads we have too, in 101, we have a main thread, we have a thread 1 and thread 2. In 102, it was kind of like a copy of thread 1, if we want, but it only has a single thread executing in it. Yeah. Yeah, so in 102, like it clones the entire process, all the virtual memory, everything, but like all the registers and everything are specific to thread 1 in this case. So all of its local variables, everything will just be copied. So it'll just look like there's only one thread running now, but all the other memory is the same. If it accessed global variables or whatever, it'd be the same as whatever the values were whenever it was forked. So like a mean thing I could do is like create a global and then like essentially have a data race here. And then if there's a data race, the value of that will be different depending on the order of them before the fork, and that's a whole mess. So yeah, don't worry about that. But yeah, it'll just be a copy at the time of the fork. All the same fork rules apply, exact copy. All right, any other questions? All right, so now at this point, in thread 1 in process 101, what does it get returned to? what does fork return for that one? 102. So in thread 1 and 101, here I'll use a different color. PID is equal to 102, and in process 102, PID is equal to 0. So now at this point, do I know if process 102 is going to run or thread 1 in 101 is going to run? No idea, up to the gods. So which one do you want to do? 102? All right. So 102 will execute this print line. So what will we see in this print line? So it will print thread and then thread ID. What is thread ID in process 102? 1. So thread ID is 1, and then it would say running da 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 da, and what's its process ID? 102. And then in that case, well, PID is not greater than 0. It is 0, so it's just going to hit return null. If you return from your thread function, what is that the same as doing? pthread exit, right? So it's like the exact equivalent for just the main function. So if you return from main, that's the same as calling exit. And for your thread function, if you return from your thread function, that's the same as calling pthread exit. So in this case, if 102 goes ahead, returns, it was the exact copy of that thread at the time of the fork, so it's just going to call pthread exit. And in process 102, there was only a single thread running, and it called pthread exit. So what happens if you call pthread exit and you're the last thread alive? Yeah, then it just calls exit. The process is now donezo. So 102, I can thankfully delete. At this exact moment, what is the state of process 102? Is it a zombie? Is it an orphan? Is it chillin'? Zombie, right? At this exact moment, it is a zombie because it has now terminated, but no one has successfully waited on it yet. So 102 still exists, but I'll just put an X beside it to say that it is terminated, hasn't exited yet. So now at this point, let's say thread 1 in 101 continues executing. It would hit this print statement. What would it print? So it would print thread what? Thread 1 running in process what? 101. And then it is going to check, is PID greater than 0? Yes, it is currently 102. So it's going to call wait PID on 102, which will wait until it's terminated. Hey, right now it's already terminated. Great. So now we can clean it up. It is now just dead. So here, I'll just put it in, I don't know, this color. So 102 is now just completely deleted. We could also reuse the PID if we really wanted, but we can keep our lives less complicated and just say it's just gone. So thread 1 would go ahead and then return null. So that means thread 1 in process 101 is now gone. So is there other threads executing in process 101? Yeah, so this thread's just gone. It's technically a zombie thread right now, but if we start executing 101, well, it can make it past this join because thread 1's now done, and we just cleaned it up, and the main thread of process 101 is now stuck in join for thread 2. So any questions about that? So let's see, can I do this? Oh, geez, we're kind of out of time. All right, if I do this on turbo mode, well, thread 2 is going to do the same thing except create another process probably called 103. So we'd get 101, 103, thread. So that would be all them that's derived from process 101, and this entire thing is going to happen again for process 100. So process 100 is going to make 2 threads, and then each of those threads is going to make a process, and it probably looks something like this. and then we would get the same thing. So thread 1 would print from process 100, thread 2 would print from process 100, and then thread 1 would probably print from process 104, and thread 2 from 105. But those numbers just come down to luck at that point. As long as they're consistent, so there'll be always a thread 1 and 2 from process 100, and a thread 1 and 2 from process 101. Aside from that, you'll just have different orderings of them. As long as your numbering is consistent, it doesn't matter. Yeah.
Like, let's say, like we kill, or like a process terminates.
Mm-hmm.
Can't we reuse that PID like when we make another process?
Yeah, technically, if you wanted to, you know, thread 1 could run, create a process, clean it up, and then thread 2 could run and then create another process with the exact same ID because we can reuse it. So yeah, if you really want to make your graders really happy, you could do that. Technically, it would be right. They would probably look at it, and you'd probably have to get corrected because they'll probably look at it and do like the typical pattern matching thing and be like, no, wrong. And then you'd be like, actually, that you can do that.
Okay, but your suggestion is not to do that?
Yeah, generally make the grader's life easier, and they'll be much happier and probably more lenient. So like imagine if you're grading something, if you're like grading like 10 pages of chicken scratch versus like 2 sentences, probably like the 2 sentences a lot more. All right, any other questions? Oh, we only have a minute, damn. All right, so, oh yeah, also for the Wednesday practicals, I will probably be around in the practicals whenever the hell I get to Toronto. So if you want to come ask me questions there, I assume it'll be the day of the midterm and people will leave things for last minute, so you can come swamp me in whatever rooms those are there. So with that, just remember, pulling for you, we're all in this together. And the midterm won't